Greetings, friends of chemistry. This is practice problem number 3 for module 13. Please read it, Martin.
When coal is burned in a power plant, it usually contains a small amount of sulfur contamination. The sulfur burns along with the coal to make SO2. This sulfur dioxide then begins to travel up the smokestack, where it reacts with oxygen as follows. 2 SO2 gas plus O2 gas yields 2 SO3 gas. If the delta H degree of this reaction is negative 198 kilojoules,
Okay, so that's the standard.
If the standard enthalpy of this reaction is negative 198 kilojoules, what is the standard F degree?
Okay, so this is the standard change in enthalpy.
Standard change in enthalpy of SO2 gas.
It equals what?
What equals what?
Oh, we don't know what it equals. Okay, so we want to find it, right?
Oh, we know that.
No. Okay, what is it then? It's negative 198 kilojoules. So what do we want to find out?
The standard change in enthalpy.
We want to find this. That's not what we want to find. We want to find the standard enthalpy of formation.
Okay, standard enthalpy of formation.
Of what?
Of SO2 gas.
Okay, so how do we calculate the standard change in enthalpy? It equals the summation
of the formation of enthalpy products minus the summation of the standard formation of enthalpy of formation of the reactants.
Yes, so we say the summation of the standard enthalpy of formation of the reactants minus, is that correct? The products minus reactants, right?
Yeah.
Sorry, I'm writing wrong. Products minus the summation. Where is it? Give me that symbol so that I can write this silly thing. My poor little brain. It's not working well. Poor mother. Okay, so what is this going to be?
It's going to be
0, because this is the elemental form. So the standard enthalpy of formation is going to be 0.
Yeah.
The standard enthalpy of formation of this is what we need to calculate, right?
Yeah.
So how can we find out the standard enthalpy of formation of the SO3? Where are we going to find that? Is that in our chart?
Yeah.
SO3 gas is, what is it?
Negative 398.
It's negative 398 kilojoules per mole. Okay. So that is our product. So there's only one product. So it's going to be equal to 2 moles times 398 kilojoules per mole minus whatever this is, right?
2 moles.
And all this is going to be is the standard enthalpy of formation of SO2, because there is no, this is 0, right? And what does it equal? It equals negative 198.
Mm-hmm. So the standard
kilojoules.
enthalpy of formation of SO2 equals 198 kilojoules minus 2 times 396 kilojoules over negative 2 moles.
So
Which equals 297.
did you multiply 2 times 200? 396? Why did I have 398?
I don't know.
It's 396. Sorry, what's the SO3? 396. Okay,
Yeah.
that's right. 396, 396. So what's 2 times 396?
It's 790.
Two, right?
Yeah.
Okay. And then we add it to both sides. So we have 792 minus 198. How come I have something different?
I don't know.
Different from you. Oh, of course, because there's 2 moles of this. So whenever what I get here, then I'll divide it by 2 because I forgot that there was 2 moles of this.
Yeah.
Okay? So this needs to be 2 moles divided by. So what do I get here? 4, 9, 297 kilojoules is the standard enthalpy formation of SO2.
Yep.
Okay? Let's try for number 4 in this same video.
Okay. Using the delta H you got in number 2, calculate the number of kilojoules of energy released when 500.0 grams of benzene are burned in excess oxygen.
Okay. So number 2 is in a different video. I'm going to erase all of number 3 here. What was the answer that we got in number 2?
Negative 6,278 kilojoules.
Negative 6,000, sorry,
278 kilojoules.
78 kilojoules. Okay, this is number 4, and this was the answer we got. That was the delta H that we found.
Yeah.
The standard change in enthalpy. Okay.
Yep.
So 500.0 grams of benzene, which was what, C6, what was it?
It was
C6H2?
C6H6.
C6H6. Okay. So what do we have to know here?
We gotta know the kilojoules of energy released.
Okay. So let me just ask, since this is a negative number, what does this tell us?
That it's an exothermic reaction.
Standard change, just change in enthalpy. It tells you that it's a product of the reaction, right?
Yeah.
So what would it look like if we wrote it as a product? Let's go back and look at the equation we wrote in number 2. We said, I don't remember. Can you give me the balanced equation?
2C6H6 liquid plus 2H2 plus 15O2 gas yields 12 CO2 gas plus 6 H2O gas.
Okay. So, and then we're going to put in our kilojoules, plus 6,278 kilojoules.
Yeah.
Okay. Now, let's do some stoichiometry and figure out how many moles is 500.0 grams. C is how much?
6.40 moles.
Okay.
Of
What is the carbon weight? Carbon is. We're doing stoichiometry here. I want to know how many grams. How many moles is these grams?
Oh,
What's the weight of carbon things?
Right. Carbon is 12.0.
And hydrogen
is 1.01.
So that gives me 72 and 6.06 gives me 0.68. So that yield rounds to 78.1, right?
Yeah.
Grams per mole, or 1 mole per gram. So 500 grams times 1 mole per 78.1 grams. So grams will cancel. So please divide 500.0 by 78.1.
We got 6.40 moles of C6H6.
Okay, and that is accurate to 3.
Yep.
Good. Okay, so now what? For every 6.40 moles, okay, for every 2 moles of this, look, how much energy? 6,278. So if we have 6, so what's the relationship? 2 moles
per
6,278 kilojoules per 2 moles, or 2 moles per 6,278 kilojoules, right? Either of these relationships. So which relationship do we want here? We have 6.40 moles.
Kilojoules to moles.
Yeah, so we're going to multiply it by 6,278 kilojoules per 2 moles. Moles cancel. I divide by 2. I get 3, 1, 3, 9. So you multiply that by 6.4. And we want 3 significant digits, I mean.
20,100 kilojoules.
20100.
Yep.
Kilojoules. Okay. Should we leave it like that? Does that express it correctly with the correct number of significant digits? Yeah, we have 1, 2, 3 digits. That's okay. The other way you could do it would be 2.01 times 10 to the 1, 2, 3, 4, 4th kilojoules. Either of these is correct. So for every 500 grams of benzene, you have this much energy, kilojoules. Alrighty, and that's it for number
4.